Hello and welcome to the AICE Chemistry lecture series. In this video, we're going to look at chapter 14, section 4, which is a bit of a review of bonding, but specifically when it comes to organic compounds. So we're going to revisit some topics like sigma and pi bonding from earlier chapters, but we're not specifically look at how it applies to organic compounds and the carbon bonds that are made. So let's start. So whenever we have bonding of carbon, carbon has the electron configuration 1s2, 2s2, 2p2, meaning that in its valence shell, carbon has 4 valence electrons. According to the octet rule that we learned earlier, because carbon does not break the octet rule, then we're going to have 4 bonds that are created by carbon. Because of this, carbon needs 4 more electrons in its valence shell to have a full valence octet. So we're going to need 4 covalent bonds in order to achieve that. All right. So whenever carbon bonds in an organic compound, it's always going to consist of 4 bonds whenever it has a neutral charge. And this is something that we saw earlier in earlier sections. So whenever carbon bonds, there's really only 4 choices that come about that. We could have carbon form 4 individual single bonds to create that valence electron shell. And when this happens, the shape that forms around that carbon is going to be tetrahedral. So whenever carbon forms 4 bonds, the farthest those 4 individual bonds can be away from each other are 109.5 degree angles, forming that tetrahedral structure that we learned earlier in the year. If carbon has a double bond and 2 single bonds to form that octet, then we're going to get a trigonoplanar carbon, where the bond angles are roughly 120 degrees. Roughly, a little less, a little more sometimes. That's going to happen anytime carbon has a double bond and 2 single bonds, meaning this is going to be a flat molecule. Or a flat section of the molecule, should I say, because organic molecules are made out of many carbons. If you have 2 double bonds, then we have a linear section of a molecule with 180 degree angles. And the same thing happens when we have a triple bond along with a single bond on the carbon. So both of these are going to be linear. So out of all of the different shapes that carbon can form, the only one that's actually 3-dimensional in nature is the tetrahedral. The trigonoplanar, linear, and both the linear carbons are going to be flat on the plane of the molecule. So the tetrahedral carbons are the only ones that are going to be kind of 3-dimensional. The shape of the bonds on the carbon is going to essentially depend on whether we have single or double bonds or triple bonds, meaning it's going to depend on whether we have sigma bonding or pi bonding in those carbons and how much of it. So remember, sigma bonds and pi bonds are something we discussed earlier in the year, but they essentially are going to happen whenever we have sigma bonds going to happen whenever we have a single bond, as well as one of a double or triple bond, and then the pi bond is going to happen for everything other than that sigma bond in double and triple bonding. So let's dive a little more in depth into that idea of sigma and pi bonding in an organic compound. Sigma bonding in an organic compound is going to happen whenever we have single bonds. So as well as one of the multiple bonds. So one of the 2 bonds in double bonds, or one of the 3 bonds in triple bonds are going to be sigma bonds. If you remember, whenever a molecule has only sigma bonds, whenever a carbon has 4 sigma bonds, that's going to result in sp3 hybridization. Now, I'm not going to go too much in depth into this because this is something we covered earlier in the year, but sp3 hybridization happens whenever a bond is created from the mixture, whenever an orbital is created from the mixture of 3 p orbitals and an s orbital. Whenever we have these orbitals being mixed, we're going to create 4 sp3 hybrid bonds or hybrid orbitals. Those hybrid orbitals are what carbon actually uses to bond. Carbon does not use s or p orbitals to bond. Those are only present in carbon in its atomic form. Whenever carbon actually goes to bond, the hybrid orbitals are created by mixing those atomic orbitals. So these are atomic, the s and p orbitals are atomic orbitals, whereas the sp3 orbitals are what we call hybrid orbitals that are formed specifically for the purpose of bonding and creating those tetrahedrals. Those sigma orbitals are going to contain, those sp3 orbitals are going to contain the electrons that are going to be used for the bond. And then when they overlap with the orbitals on the hydrogen, which are just s orbitals, they're going to create that sigma bond where the bonding happens. And the sigma orbitals, what we can call it as well. So because those electrons, so every one of these bonds, so let me highlight a few things here. Every one of these bonds right here, these are all sigma bonds because they're all single bonds. Single bonds are always going to be sigma bonds. Now, because of how bonding happens, I'm actually going to use two different colors here, now that I think about it. Because of how bonding happens, we have two different kinds of sigma bonds here. The sigma bonds between the carbon and the hydrogen, the yellow ones, are going to be the result of an s orbital overlapping with a hybrid orbital. So the hybrid orbital from, let me make that a little smaller. So the hybrid orbital from the carbon overlaps with the s orbital from hydrogen. Remember, hydrogen does not have hybrid orbitals because it doesn't have any p orbitals to hybridize. So the actual sigma bond that we see here being created between carbon and hydrogen, and that's true of all of these yellow ones, happens because of the overlap of the hybrid sp3 orbital from carbon with the s orbital from the hydrogen. On the other hand, the bonds created by the, let me use a different color here. The bonds created between carbons, the ones in pink, are the result of the hybrid orbital from carbon overlapping with the hybrid orbital from the other carbon. Now, this is still a sigma bond because it's a single bond and is a result of end-to-end overlap, which is what classifies a sigma bond. But it is a sigma bond created from a different connection. So the connection in yellow here, or the one in blue, is the result of an sp3 hybrid orbital from carbon overlapping with the s orbital from the hydrogen. On the other hand, the ones in red, the ones between carbons, are the result of the sp3 hybrid orbital from carbon overlapping head-to-head or end-to-end with another sp3 hybrid orbital from a different carbon. Like I said, these are still both sigma bonds. They're just different types of sigma bonds. So whenever this occurs, whenever the sigma bonding happens, we are gonna end up with tetrahedral carbons here because they're all single bonds. These are all sigma bonds. Each carbon has 4 single bonds. So we end up with tetrahedral carbons. That's where we get that zigzag shape of the carbons. Because if you look at any one of these, we can see that we have the tetrahedral. They're just in different orientations. So these are the tetrahedral structures that we get around those carbons when they all have only sigma bonds from single bonds. So every one of those, just to show, every one of these bonds, whether they're going forward if they're wedges, or they're going back away from you if they're dashes, or if they're on the plane, these are all sigma bonds. So we show those by some kind of oval. Usually if we're trying to be more precise, we will show this oval with a little tail here to signify the tail from this hybrid orbital, whereas the ones for between carbons both will have a tail both sides because both of them were hybrid orbitals. but we're not being that specific with this drawing here. So that zigzag pattern is actually the zigzag pattern we see in the skeletal structure of this molecule. If we were to draw this molecule, which by the way, if we remember from nomenclature, this will be pentane, because that's 1, 2, 3, 4, 5 carbons, all single bonded, nothing but hydrogens on them. So this will be pentane. Pentane is drawn in this kind of zigzag W shape, and that's because of that structure behind the carbons, because they're all tetrahedral in nature. All right. So let's move on now to pi bonds. Now, pi bonds are a little more tricky. Pi bonds only happen whenever we have double or triple bonding. Double bonds and triple bonds are always going to contain one sigma bond. And the bonding axis, being the bond that we're actually drawing, that is going to be our sigma bond. But then when we have a double bond or even a triple bond, we are going to have a pi bond happen above and below the axis. Now, if you remember, a pi bond here is going to happen for one of these double bonds. So each double bond has one pi bond, and then the sigma bond that we just talked about is going to be the other bond on the double bond. Every single bond is therefore a sigma bond, whereas double bonds have one sigma and one pi bond. And then we don't have an example of it here, but a triple bond would have one sigma and two pi bonds. So we already discussed how the sigma bonds happen, right? They're the result of the overlap of either hybrid orbital from the carbon and the s orbital from the hydrogen, or in the case of two carbons, they're the result of hybrid orbitals overlapping. But the hybrid orbitals for a carbon with a double bond are actually a little different, because hybridization for a double bonded carbon is not going to be sp3 hybridized. The hybridization for a carbon with a double bond is going to be sp2 hybridized. Why is that the case? Well, first of all, let's go back and kind of review what an sp2 hybrid orbital is. sp2 hybrid orbitals are going to be the result of mixing the atomic orbitals that are s and 2p atomic orbitals. That's going to result in 3 sp2 hybrid orbitals. Now, because that sp2 hybrid orbital only uses 2 of the p orbitals, and every valence shell has 3 p orbitals, that means not only do we have that sp2 or the 3 sp2 hybrid orbitals in a carbon, we also have a p orbital. And that p orbital is necessary because that p orbital is what forms our pi bond. Remember that pi bonds that we're showing here in yellow can only be the result of p orbitals overlapping side to side. Let me do a better job of drawing that there. So a pi orbital is going to be the result of the side to side overlap of p orbitals. So when p orbitals overlap side to side like this, they form a pi bond. And that pi bond has 2 lobes, just like the p orbitals do, but it's going to be one above and one below the sigma bond that's being created. So this is going to result in different shapes. Whenever we have a double bond and 2 single bonds on a carbon, that carbon is going to be trigonoplanar in shape. So let me erase these colors so we can see it better. So whenever we have that overlap, the carbon that has a double bond is actually going to be trigonoplanar in shape. We see this triangle shape instead of tetrahedral. Why? Because of the pi bonding. And it's the same thing here with any carbon that has 2 single bonds and a double bond. Now, if a carbon does have 2 double bonds like this one right here, then that is going to give you a linear shape because of the pi bonding. So let's look at what that pi bonding looks like, right? So this is the sigma bonds that are created in gray and black and white, like we saw earlier. And so the carbons that have the double bonds have one sigma bond, because remember that every where it's a single, double, or triple bond, it always has one sigma bond. But the double bonded carbons also have a pi bond. Now we represent that pi bond as these two, in this case red, ovals above and below the bond. But remember, both of these ovals together are one pi bond. This is not two different pi bonds here. These are together, one pi bond, not two. So in this one, when we have two double bonds, both of the red ovals are one pi bond, which is the pi bond created between these two carbons. And then both of the blue ovals on the other side are going to be another pi bond for the other double bond. So this creates flatter areas to the molecule. Pi bonds bring a lot to the table because they're not only just going to flatten out the molecule, like we see here and here, but they're actually areas of really high electron density. What do we mean by that? Well, there's simply just more electrons, right? A double bond has 4 electrons as opposed to the 2 electrons in a single bond. So these areas of lots of electrons are actually going to be the centers for chemical reactions once we go into chapter 15. But we won't touch that right now. So what happens here? A carbon with one double bond, meaning one pi bond, gets straightened out a bit. And so these carbons are all trigonoplanar, whereas the carbons with two double bonds, like the center one here, is going to be linear in shape. These are a lot less common because electrons don't like being that close to each other, but they do happen from time to time. So just so we can again see the comparison between these, let me erase this. Just so we can see the comparison, if we go back, notice we have that double bond, two double bonds here, and this, so instead of being tetrahedral like this carbon, we have a trigonoplanar shape in this carbon. And for this carbon, which has two double bonds, it's linear in shape. And all these carbons have different hybridization. This carbon will be sp3 hybridized because it has 3 single bonds. This carbon will be sp2 hybridized because it has a double bond and single bonds. And this carbon right here would actually only be sp hybridized. Why sp hybridized? Because in order to have two double bonds, like I mentioned earlier, the pi bond in a double bond can only be formed by this p orbital up here. So that p orbital that's left over from the hybridization actually goes to creating a pi bond. So if we have two pi bonds on a carbon, we need two p orbitals that are intact. So whenever a carbon has two double bonds, instead of being sp hybridized, it will be instead of being sp2 hybridized, it will be sp hybridized. We will actually get rid of one of the p's in the hybrid orbital, make two sp hybrid orbitals, and then that frees up that extra p orbital that we talked about earlier to then make a second pi bond. That second pi bond being in the other double bond. So carbons that have two double bonds or carbons with a triple bond will be sp hybridized instead of sp2 or sp3. So again, we go and we look at this. So here we can see that shape in our skeletal formula where we have those flatter areas in the molecules thanks to the trigonoplanar shape for the sp2 hybridized carbon and the linear shape of the sp hybridized carbon. All right. So that's pi bonding in double bonds of these compounds, of these organic compounds. Now let's take a quick look at what happens with that triple bond that we talked about earlier. So in triple bonds, we contain, again, one sigma bond, because it's always going to be a sigma bond. Doesn't matter if it's a double, triple, or single bond. There's always going to be a sigma bond in these. So out of that triple bond, that one bond is sigma. And all of these single bonds are always sigma, because every type of bond, whether single, double, or triple, has a sigma bond. On the other hand, there are 2 pi bonds in a triple bond. The other 2 bonds in a triple bond are going to be pi bonds. So in this sigma bond, this triple bond, we have 1 sigma, 2 pi. The sigma bonds are going to consist of sp hybridized orbitals. So these carbons right here that we see have the triple bond, these are going to be sp hybridized carbons. And then we just talked about this. So this is sp, this is sp. Whereas this carbon is sp3 hybridized because it has 4 bonds, 4 single bonds. So these are sp hybridized. That means that in order to create their hybrid orbitals, the atomic orbitals that were mixed together was 1 s and 1 p orbital to create 2 sp hybrid orbitals. And these are the ones that are used to form those sigma bondings. So the sigma bond here in yellow is formed by an sp hybrid orbital from this carbon, overlapping with an sp hybrid orbital from this carbon. And then this one right here is formed by that sp hybrid orbital from this carbon, overlapping with the sp3 hybrid orbital from the other carbon. Notice that even though this is sp3 and this is sp, the hybrid orbitals always have the same shape. It's had kind of like a half p orbital shape. So why does this happen? Again, this happens because that leaves our 2p orbitals from the atomic orbitals, because always 3, free to create 2 pi bonds. We need 1 p orbital for one pi bond, 1 p orbital for the other pi bond in this triple bond. And that's why the sp hybridization happens. So if we look at the 3-dimensional shapes, what that triple bond does is that it makes that part of the molecule flatter. Because a triple bond means that that carbon can only have 1 other bond, and the farthest 2 bonds can be away from each other around an atom is 180 degrees. So that triple bond and the single bond are 180 degrees from each other, making both of these carbons linear. So that creates these big flat areas in molecules. Now, when we look at the pi bonding, again, the sigma bonding is that gray area that we see here in the middle that's created by the sp hybrid orbitals. The green, which has 1 lobe of the pi bond in the front and 1 lobe in the back, that is one of our pi bonds. And then the blue above and below is the other pi bond. Remember, a pi bond consists of 2 lobes, 2 or what are these called? Ovals, that's the word. They consist of 2 ovals. So the 2 green ovals, the white with green and the shaded in green, that's 1 pi bond. And the 2 blue ovals, the white with the blue and the shaded in blue at the bottom, that's another oval. So that creates that flat area. So this is a better look at it from kind of like the side. You have that gray sigma bond in the middle connecting the 2 carbons. And then you have 1 pi bond above and below. So let me color code these. So we're going to have 1 pi bond above and below. So the 2 blue ones are 1 pi bond. And then another pi bond in front and behind, which I'm going to color code here with pink. So that's the 2 pink ones are 1 pi bond. The 2 blue ones are a separate pi bond. So this is 2 pi bonds in total and 1 sigma bond in the middle. So let me put in the sigma bond here. The sigma bonds are made from the sp hybrid orbitals. The pi bonds are made from those p atomic orbitals. And this creates all a very flat molecule that has 180 degree angles for both of those carbons. So that's why the skeletal structure, the skeletal formula for this compound looks like this. It's flat. All right. So that's pi and sigma bonding in a gist. Again, these are pi and sigma bonding as well as hybrid orbitals and the Vesper shapes are topics that we covered earlier in the year. So this should be a good review for the upcoming AICE exam. But it is now specifically adapted or specifically applied to organic compounds and organic molecules and why the skeletal structures look like they do. Well, that's it for this video. I will see you all in the next video so we can start talking about isomers in 12.5.